Welcome to Tech Girl Kannada YouTube channel. Lasers. The word laser is an acronym for light amplification by stimulated emission of radiation. Lasers produce highly directional and highly intensity beam of with a narrow frequency range. The first laser was built by Theodore H. Myman T.H. Myman in the year 1960. Many scientific, military, medical, and commercial applications have been developed since its invention. Characteristic properties of a laser beam. Directionality. A laser light is highly directional. This means that the light emitted by the laser does not show much divergence. Monochromaticity. This means all the photons in the laser beam are of the same frequency. The monochromaticity of the laser light is 10 million times more than the sodium light, which is also monochromatic light. Coherence is a major optical property of laser that exists due to stimulated emission. It simply denotes that the wavelength of the waves emitted at light is in phase. When we talk about the ordinary light source of, for example, LED, then it does not show the property of coherence because it gets generated due to the process of spontaneous emission of photon. Wavelength of the waves emitted are in phase. Intensity of the laser light has degree. Due to continuous reflections, a light of high intensity and more power is produced by laser. The resultantly allows the generation of bright light through the device. The intensity of helium neon gas light laser light is 100 to 150 times more than the sunlight when both are emitted per same area. Focusability as laser beam is highly monochromatic and collimated. It can be brought to the sharp focus using lens. Focusability of laser light is 100 times more than that of the ordinary light due to the above characteristics. Interaction of radiation with matter in terms of Einstein A and B coefficients. As you can see in the figure, the first one is induced absorption. An atom residing in the lower energy level, E1, may absorb incident light and jump to the excited state, E2, as shown in the figure. This transition is known as induced or stimulated absorption. Corresponding to each absorption transition, one photon disappears from the incident light and one atom adds to the population of the excited energy level. This process may be represented as A plus H nu gives A star, which means an atom which is residing in the lower energy level absorbs the incident light and jump to the excited state E2. This transition is known as an induced or stimulated absorption. Corresponding to each absorption, the one photon disappears from the incident light and one atom adds up to the population of the excited energy level E2. This process is called induced absorption, where A denotes an atom in the lower state. A star is an atom in the excited state. As you can see in the figure, E1 to E2. H nu is E2 minus E1, the energy difference. The rate of absorption occurring in the material at any instant is proportional to the population in the lower energy level and the number of photons per unit volume. Energy density. The rate of absorption occurring in a material at any instant is proportional to the population in the lower energy level and the number of photons per unit volume. Energy density in the incident beam. Thus, the rate of absorption may be expressed as R abs is equals to B12 U nu N1, where B12 is a constant of proportionality, U nu is the energy density of incident light. B12 is called the Einstein coefficient for induced absorption and indicates the probability of induced transition from 1 to 2. Spontaneous emission. If an excited atom is not stimulated by any other agent during its short lifetime, it undergoes a transition to the lower level on its own. During this transition, it gives up the excess energy in the form of photon as shown in the figure. This process in which an excited atom emits a photon all by its own itself and without any external impetus is known as spontaneous emission. This process is represented by A star gives A plus H nu. before and after the energy, the atom will be in the excited energy level, and then after the short lifetime, it undergoes a transition to the lower level on its own, emitting a photon. There's h nu, emitted photon h nu is energy difference E2 minus E1. The rate of spontaneous emission depends on only on the population of the excited level. Thus, the rate of spontaneous emission may be expressed as RSP is A21 into N2, where A21 is called Einstein coefficient for spontaneous emission. It indicates the probability of spontaneous transition from 2 to 1. Stimulated emission. If a photon with appropriate energy, h nu E2 minus E1, interacts with if a photon, okay, there's another photon. If a photon with appropriate energy E2 minus E1 interacts with the excited atom, it can trigger the atom to undergo transition to the lower level. It triggers the atom to go to the lower level and to emit another photon as shown in the figure. The process of emission of photons by an excited atom through a forced transition occurring by the influence of external agent is called induced or stimulated emission. This process may be represented as A star plus h nu is equal to A plus 2h nu, as shown in the diagram, where a photon with appropriate energy, that is h nu is equals to E2 minus E1, interacts with the excited atom, which triggers the atom to undergo transition to the lower level and to emit another photon. This process of emission of photons by an excited atom through a forced transition occurring under the influence of external agent is called stimulated emission. The rate of stimulated emission is proportional to the population of the higher energy level and the number of photons per unit volume in the incident beam. Number of photons per unit volume in the incident beam. Thus, the rate of stimulated emission may be expressed as RST is equals to B21 U nu N2, where B21 is Einstein coefficient for stimulated emission. Expression for energy density. Under the thermal equilibrium condition, the mean population N1 and N2 in lower and upper energy levels, the mean population remains constant. This condition requires the number of transition from E2 to E1 must be equal to the number of transition from E1 to E2. The number of atoms absorbing photon must be equal to number of atoms emitting photons per second per unit volume. Therefore, at thermal equilibrium, the rate of absorption is equal to rate of spontaneous emission plus rate of stimulated emission. B12 U nu N1 is equal to A21 N2 plus B21 U nu N2. That is, rate of absorption is equal to the rate of spontaneous emission plus rate of stimulated emission. B12 U nu N1 gives A21 N2 B21 U nu N2. U nu B12 N1 minus B21 N2 is equals to A21 N2. U nu is equals to A21 N2 by B12 N1 minus B21 N2. By rearranging the above equation, we get that U nu is equal to A21 by B21 1 by B12 N1 by B21 N2 minus 1. But by Boltzmann's law, we have N1 by N2 is equals to E power E2 minus E1 by KT, where E2 minus E1 is equals to H nu. N1 by N2 is equals to E power H nu by KT. Yes, C21 is even H nu. N1 by N2 is equals to per H T21 N by KT, H nu by KT. Substituting N1 by N2 in the equation, we get U nu is equals to A21 by B21, 1 by B12 by B21, e power H nu by KT minus 1. To maintain the thermal equilibrium, the system must release energy in the form of electromagnetic radiation. It is required that the system must release energy in the form of electromagnetic radiation. That is required that the radiation should be identical to the black body radiation and consistent with the Planck's constant radiation law for any value of the temperature. According to Planck's law, we have U nu is equals to 8 pi h nu cube by c cube, 8 pi h nu cube by c cube to 1 by e power h nu by kt minus 1. By comparing equations 5 and 6, we get b12 by b21 is equals to 1, or b12 is equals to b21, and a21 by b21 is equals to 8 pi h nu cube by c cube. Equations 7 and 8 are known as the Einstein's relations or Einstein A and B coefficients. Einstein's relations for Einstein A and B coefficients. Putting b12 by b21 is equals to 1 and dropping the subscripts a21 and b21. Equation 5, we get u nu is equals to a by b into the denominator e power h nu by kt minus 1. This is the expression for energy density. Also, the equation a21 by b21, 8 pi h nu cube by c cube, signifies the relative probability. Yes, signifies the relative probability for spontaneous emission increases with increase in the cube of the frequency of emitted photons. Signifies that the relative probability of spontaneous emission increases with the increase in the emitted photons. This indicates that it is difficult to produce laser light of higher frequencies. That is why we rarely see blue and higher frequency lasers. Conditions for laser action. The condition for laser action, there are two conditions, namely the population inversion and the metastable state. Population inversion, which means that it is the non-equilibrium state in which the population of N2 of the upper energy level exceeds the population of N1 of the lower energy level. It is known as state of population inversion. The figure A represents that population of three states in which the N3 is lesser than N2 is lesser than N1, the system absorbs photon rather than emitting. However, if the system is supplied with external energy, that is N2 exceeds the N1, we say that the system has reached population inversion. Here the population inversion has taken between the A2 and E1 as shown in the figure B. Under the population inversion condition, the stimulated emission can produce cascade of light. The first few randomly emitted spontaneous photons trigger the stimulated emission for more photons, and stimulated photons induces still more photons, and so on. Light gets amplified. Figure first one is under a thermal equilibrium, that is a B population inversion at a non-equilibrium state. Metastable state is nothing but the atom which can be excited to higher energy level with supply of energy. Normally, at the excited state, the atoms will have short lifetimes, release their excess energy about 10 power minus 9 seconds by spontaneous emission. Thus, the population inversion cannot be achieved. For establishing the population inversion, the excited atoms are required to stay there at least for an appreciable time. Such long-lived upper-level atoms remains for an appreciable time are called metastable states. Atoms stay in metastable state for up to 10 power minus 6 to minus 3 seconds. The metastable population can exceed the population of the lower level and lead to the state of population inversion. The requisites for laser system. There are 3 requisites as follows. Excitation source. Excitation source is very essential for excitation process, that is namely optical, electrical and chemical sources. Active medium, a quantum system between whose energy levels, pumping actions and laser actions occurs. Laser cavity, the system containing an active medium with 2 mirrors. The one is fully reflecting, another one is partially reflecting. It's called laser cavity. The mirror reflect the photons to produce the stimulated emission through the medium. The mirror arrangement ensures that the photons move parallel to the axis. If the photon moves in any other direction or it escapes from the cavity, hence the radiation inside the laser cavity builds up, leading to amplification of photons in only one direction. There are 3 requisites for laser actions, and that is excitation source, active medium, laser cavity. Excitation source, optical, electrical, chemical. Active medium, it is a quantum system between whose laser actions, energy levels pumping takes place. And laser cavity containing active medium with 2 mirrors, one is fully reflecting, the other one is partially reflecting. The mirror reflects the photons to produce stimulated emission through active medium. The arrangement ensures that it moves parallel and the radiation inside the laser cavity builds up, leading to the amplification of photons in only one direction. Then types of lasers. We have four types of lasers, that is solid lasers, liquid lasers, gas lasers, semiconductor lasers. These types. Then if we consider the active medium, the first one, active medium for solid laser is crystalline materials, glass and ceramic materials. For active medium of liquid lasers, are liquid, usually organic dyes. Gas medium, active medium is mixture of gas. Semiconductor laser for semiconductor compounds. And if we consider the pumping mechanism, first one solid laser, usually it will be optical pumping, and for liquid laser, optical pumping, electrical pumping, chemical pumping. Along with that, the chemical reactions. The gas lasers, optical pumping, electrical discharge pumping, chemical pumping, microwave pumping, radio frequency pumping. And for semiconductor laser, it is electrical injection pumping, which means the forward biasing. Optical pumping, electrical injection pumping. Now the examples of solid lasers: ruby laser, ND arc laser, ER arc laser, and liquid laser, dye lasers, rhodamine 6D dye laser, rhodamine B dye laser, and also rare earth ion lasers. Then again, gas lasers, helium neon lasers, carbon dioxide laser, argon ion laser. For semiconductor, gallium arsenide laser, quantum dot laser. This ruby laser used in eye surgery, cutting, welding, etc. And the YAG laser, cutting, welding, range finding, etc. For YAG laser, 3D printing, precision machining. And this dye laser is used in spectroscopy, skin treatment, and cancer treatment. This rare earth ion laser will be used in dental procedure, ophthalmology, helium neon laser, skin treatment, fiber optic communication, holography. And this carbon dioxide laser, cutting and welding, argon ion laser, material processing, gallium arsenide laser, laser printing, CD player, quantum dot laser, data storage and optical communication. The semiconductor laser, explanation of this semiconductor laser. The first thing is gallium arsenide semiconductor diode laser principle. What is the principle of this semiconductor laser is, when the p-n junction is forward biased, the electron from the n region and the holes from the p region cross the junction and recombine with each other. During recombination, the light radiation is released. In case of specially fabricated p-n junction. Now we shall see the construction. Construction is very easy, that it is formed by the doping of aluminium or silicon with the gallium arsenide to generate the n-type and p-type. Along with that, an additional layer which is present in between the 2 layers, that is undoped region, active layer called undoped region. The thickness of the active layer is 10 to 100 micrometer, and the length and breadth is 1 centimeter. The aim of sandwiching this layer in between p and n-type is to help with the help of power supplies to increase the electron hole recombination, resultantly increasing the emitted radiation. It takes place in the laser output is taken in the laser active region only. In laser diodes, polishing at the 2 ends. In laser diodes, polishing at the two ends is done to provide the mirror-like structures through reflection. More electrons and hole pairs gets produced, resultantly produces the more radiation through the device. Now we'll see the working of this semiconductor laser. When PN junction is forward biased with a high voltage, electron holes are injected to the junction. Then the region around the junction contains like large number of electrons in the conduction band and large number of holes in the valence band. If the population density is high, population inversion is occurred without the aid of metastable state. Due to stimulated emission, the electrons holes recombine with each other. The recombination produce radiation in the form of light, and the forward bias voltage is increased. More and more light photons emitted more light, and intensity becomes stronger. These photons will trigger the chain of stimulated emission, resulting release of photons in phase. The photons moving at the parallel and opposite to each other grow in strength. After gaining enough strength, it gives out the laser beam of wavelength 8400 angstrom. Now we'll again see the principle when a p-n junction diode is forward biased. The electron from the n region and the holes from the p region cross the junction and recombine with each other. Due to this recombination process, the light radiation is released. In case of specially fabricated p-n junction, construction is nothing but the doping of aluminium or silicon to the gallium arsenide under to generate this n-type and p-type. The undoped active layer is in between the two layers. The thickness is 10 to 100 micrometers, and her length and breadth is 1 centimeter long. Aim of sandwiching this layer in between the p-n junction is to, with the help of the power supply, is to increase the electron hole recombination, resultantly increases the emitted radiation. Output is taken in the from the active region of this. In laser diodes, polishing is done to provide the mirror-like structures through the reflection. More electrons or hole recombination is produced, more radiation can be obtained. Once again, we'll see the working. P-n junction is forward bias with high applied voltage. Electrons and holes injected into the junction. The region around the junction contains a large number of electrons in conduction band, holes in valence band. If the population is high, the condition of population is achieved. Population inversion is achieved due to the stimulated emission without the aid of metastable state. The electrons and holes recombine with each other. The recombination produces more radiation, and when the forward bias is increased, the light photons emitted is more, and the light production is becomes stronger. These photons will trigger the chain of stimulated radiation recombination, release photons in phase. Then in the plane of the junction, the photons travels back and forth by the reflection between the two sides, that is placed parallel and opposite to each and grow in strength. After gaining enough strength, it gives out the laser beam of wavelength 8400. Application of gallium arsenide semiconductor laser. They find applications in laser cutting, laser welding, medical equipment, industry automation, telecommunication industry, aerospace industry, military and defense. Laser cutting, gallium arsenide lasers are used because of this high powered laser beams that can cut toughest materials. Even for welding, high powered laser beams that can melt and fuse the materials. Medical equipment such as surgical lasers, that is also for high powered laser beams, controlled and targeted precisely. Industrial automation, that is used in manufacturing, assembly and packaging, which detects and measures the object's distances. Telecommunication industry, they transmit information over long distances, highly reliable, stability and low noise. Aerospace industry, they use in laser altimeters, which measure the altitudes of aircraft and spacecraft, emit light in specific wavelength that bounces to this, and the time it takes to bounce back is calculate the altitude. Military and defense, they're used in range finding, and between the measure the distance between the observer and the target. The major application of this laser is holography. Holography is a technique of capturing pictorial details of a three-dimensional object on a two-dimensional recording aid using a phenomenon called interference. The technique involves the complete recording of the pictorial details is called holography. Holo means complete, graphos means recording. The recording age on which the pictorial details are captured is called the hologram. Denis Gabor, a Hungarian-born scientist, invented holography in 1948. Holography became more practical with the development of lasers, and this mainly involves recording. Holography involves two stages of obtaining three-dimensional view of an object. There are recording and reconstruction of the image. There are two methods of recording. They are wavefront division method and amplitude division method technique. Wavefront division, amplitude division. Now we'll go for wavefront division technique. A broadened laser is obtained from the laser source with the help of lens. Okay, there is a given object whose image is captured from altering the coherence of the beam. This image is captured by mirror are placed one next to the other as shown in the figure. This is the figure where the given object and the mirror has been kept one next to the other. The expanded laser beam is then directed in such a way that a part of it incident on object and another part of it incident on mirror. Photographic film is so placed it receives reflected light. It receives the reflected light from both the mirror and the object. The light reflected from the mirror will be in the form of plane wavefront, that is reference beam. And now the part of light reflected on the object, every point on the object scatters the incident light all around. Due to such a scattering, spherical wavefront proceeds from each point on the object. A part of such physical wavefronts will fall on the photographic plate. Okay, this part is called the object beam. Now the interference occurs between the spherical wavefronts of the object beam, reference beam, plane wavefronts of the reference beam. Hence, interference effects are recorded on the photographic plate. Since the spherical wave can intersect a plane wave and circular zones, the interference pattern consists of a concentric circle pattern, that is Gabor zone plate. The ring pattern consists of successive regions of both constructive and destructive interference. Countless number of Gabor zone plates is produced and displaced from the other. The recorded pattern of all such plates is called hologram. Next, reconstruction of the image. The original laser beam at the hologram is directed at the hologram in the same direction as reference beam. Okay, the original laser beam is directed towards the same direction as reference beam. In order to reconstruct the image as shown in the figure, upon incidence, the reference beam undergoes diffraction in the hologram. Because of this diffraction, the secondary wavelengths original from each constituent zone plate which interfere constructively, they produce both real and the virtual image corresponding point on the transmission side. Since the beam is incident on the entire hologram, each and every zone plate participate in regenerating the both real and virtual image. As it appears as though the original object is lying the other side of its place, this is a virtual image due to the regeneration. But switching the direction of the view, different set of points which correspond to constructive interference are observed, which regenerate a different perspective of the object, and hence the sense of depth is felt. Now again, we quickly get into the process of this holography, that is a recording and reconstruction of the image. There are two types in recording: wavefront division, amplitude division. Now we'll get into the wavefront division, where a broadened laser light is incident on this, whose image is captured and the mirror are placed next to the other. The given object and the mirror are placed one next to the other. The expanded laser beam is directed on this arrangement. The expanded laser beam directed on this arrangement. A part of it falls on the object and on the mirror. Photographic film is placed that it receives the reflected light both from the object and the mirror. The light reflected from the mirror will be of plane wavefronts. This is called reference beam. And the part of light reflected from the object, each point on the object scatters in all the direction. Due to such scattering, spherical wavefronts proceeds from each point. A part of it falls on the photographic plate, that is called the object beam. Now the interference occurs in between the spherical wavefronts of object and the plane wavefronts of reference beam. This interference effect is recorded on the photographic plate. Since the spherical wave intersects a plane in circular zones, interference pattern consists of concentric circular ring pattern, Gabor zone plate. The ring pattern is successive, constructive, and destructive. Countless number of Gabor zone plates are produced. Each plate is slightly displaced from the other. The recorded pattern of all such plates is called a hologram. Next, the reconstruction of the image. The original laser beam is directed at the hologram in the same direction as the reference beam. In order to reconstruct the image, the laser beam, same direction. In order to reconstruct the same image, the reference beam undergoes diffraction and secondary wavelets originates from each constituent zone plates interfere constructively. Both a real and virtual image of the corresponding point of the object on the transmission side is obtained. Since a beam of light on the entire hologram, since the beam falls on entire hologram, each zone plate participates in regeneration of both real and virtual image. By seeing this, it appears as though the original object is present there, but when viewing from the different perspective of view, which regenerate the different perspective of the object. Hence, the sense of depth is felt from that. Now, we'll see the application of this holography. There are two applications, that is holographic data storage and the holographic sensor. Holographic data storage, it is a method of storing data in a three-dimensional format. Format. This method involves the data is stored in the first data is converted into 2D image. Laser is split into two beams, object beam, reference beam. Object beam is made interact with the 2D image, which creates an interference pattern. The reference beam combines with object beam, creating an hologram. The hologram is then recorded on the medium. The medium provides high data storage density, long data retention, fast data transfer, resistant to the environmental factors. Once again, we get into this thing, that is, firstly, the stored data is converted into 2D image. The laser light is split into two beams, object beam and the reference beam. The object beam is made incident on the 2D image, creating a hologram. The hologram is then recorded on the combines with the object beam, that is created hologram. Interference pattern that combines with the object beam and create a hologram. Hologram is then recorded in the medium. This method provides high data storage, fast data transfer, long data retention, resistance to the environmental factors. Holographic sensor. This works on the recording and reconstructing holograms to measure physical parameters like temperature, humidity, pressure, stress, pH, etc. A material which is sensitive to the physical quantities, such as like temperature, pressure, and all, is illuminated an object beam. A material is illuminated with an object beam. The object beam is made interfere with the. Thank you for watching. Do like, share, and subscribe to my channel.